All right, next we're going to go ahead and learn about graphing simple rational functions. So later on in math, you can learn about more complicated ones, but we're going to learn about 1 over x and 1 over x squared. So 1 over x is the most simple version. Y equals a over x minus h plus k. Is the form where you can see the transformations. And so here, this is kind of unique because instead of having a vertex or a locator point, we actually have horizontal asymptotes and vertical asymptotes. Same thing with this other parent function. We'll talk about that in class. We're just going to talk about 1 over x inside this video. So let's go ahead and graph this on Desmos so we can get some actual points, and then we'll start talking about a specific example of the problem. So 1 over x looks like this. Just a friendly reminder, we can click up here to edit the list and turn it into a table. Whenever you're graphing this on Desmos, start off right here, look for the undefined part. That's actually where the vertical asymptote is. So if you graph the line x equals 0 in this case, you can see it's because of the 0. That's where that vertical asymptote is. And then do a couple points to the left, -1 and -2, +1 and +2. That'll be the points that you can graph easily when you graph it on your paper. So I'm going to graph -1, -1, -2, -0.5, +1, +1, +2, +0.5. Those are the points that I'm going to go ahead and graph just for this first parent graph. And I'm going to go ahead, you can't see on this first example where the horizontal and vertical asymptote come from, but we're going to go ahead and graph them anyway. I'm going to use 2 different colors, and then when we do the specific example, you'll be able to see pretty clearly from the equation where they come from. So we do know from that exponential and logarithmic unit that when we graph equations that have asymptotes, that the curve gets closer and closer to the asymptotes. So I'm going to make sure that when I draw the curve that that's what I'm drawing. I'm careful to show that those curves do approach the asymptotes without crossing them. Okay, so here is our next example problem with specific numbers in there. As far as transformations go, the inside of the function is considered to be the bottom of the fraction. So if you guys recall those transformations, the part that is left, right is kind of the inside of the fraction. That's where it's the opposite of what you would think. That's the bottom right here. So even though it says +5, it's actually left 5. And then the end, just like normal, is kind of your shift up, shift down. So this would be down 3. Okay, so the left-right part is actually where our vertical asymptote goes. And so since this is left 5, our vertical asymptote is left 5. And when I reprinted these notes this year, I should have fixed this grid and I didn't even think about it. So, but it's fine. Every so often we do have graphs that are a little bit too small. And that just, it happened this year. It's no big deal. All right, and then we did have down 3, so we did left 5, down 3, which means that anytime you're looking for your vertical asymptote, it actually comes from the bottom of the fraction. So our vertical asymptote is x equals -5. The horizontal asymptote comes from the number on the end, y equals -3. So we don't have a vertex, we don't have a locator point. Instead, for this unit, we have a vertical asymptote and a horizontal asymptote, and that's what we'll be graphing this time. Okay, let's go ahead and type that equation in. Y equals 1 over x plus 5 with a -3 on the end. Since it had a 1 on the top, and that's typical for these problems, that meant that this example did not have a stretch, did not have a compression. We'll go ahead and graph that vertical asymptote there. X equals -5, y equals -3, so you guys can see it on Desmos. Okay, and then we'll go up here get that list. All right, now for the table, I know that my vertical asymptote is at -5, which means my table needs to be bigger than that. My table needs to go to a couple points to the left of -5 and a couple points to the right so that I have something to graph. So I need to go all the way to -7. So here's -5. So I need -6, -7, -4, -3 so that I have some points that I can graph. So left 6 down 4, left 7 down 3.5. So there's 2 points over there. Those are completely off the grid, so those are kind of hard to graph. And then left 4 down 2, left 3 down 2.5. All right, and then we can go ahead and look at what we've got now. So let's graph those, just getting closer to the asymptotes when we draw them, something like that. All right, so our domain represents the X values that we can see on the graph. So when you look at this graph from left to right, I can see I have all the X values that are to the left of -5, all the X values that are to the right of -5, because this goes forever, right? It just keeps going. So that means that for the domain, I need to be able to say, hey, I have all my X values, but skip -5. And the way that we write that is we say -infinity to -5, put a parenthesis because we're skipping -5. We put a U because we're putting more than one answer, and then we say -5 to infinity. So this is how we mathematically write everything except for -5. And then we're going to have a similar answer for the range. For the Y values, we have everything, but we're skipping -3 because we have that asymptote there, which means that value is not getting used. So everything beneath -3, skip -3, everything above -3. So we're going to say -infinity to -3, -3 to infinity. So the domain means everything except for -5. The range means everything except for -3. All right, X-intercept and Y-intercept we're going to get from Desmos, so I'm going to go back there and just click on those. So here's my X-intercept, there's my Y-intercept. So X-intercept I'm writing is -4.667, 0. Y-intercept is 0, -2.8. When I look at the graph, I can see that there's no max, there's no min. I don't have any mountaintops or any valleys. So for that answer, I'm going to put none. All right, next we're looking for increasing and decreasing intervals. So I'm going to go ahead and put my stick figure right here. We know that increasing and decreasing intervals both have to do with X values. So this is a left arrow that's going left forever. This arrow, it's a down arrow, but as far as talking about left and right, that's actually a -5. It doesn't go left or right, it just goes down. So that left and right value is actually -5. So this stick figure is decreasing. He hits the value of -5 and then it's like he falls off and just goes into an abyss somewhere. So a new stick figure drops out of the sky at -5. And this stick figure is decreasing and he goes right forever. So we can see that the first stick figure is between, it's decreasing, this first stick figure is between -infinity and -5. Now we have a U because we have a second answer. The second stick figure is between -5 and infinity. And then for increasing, we just say none. All right, is the graph continuous? The answer to this one's no. So we've seen continuous graphs, typically we've said yes most often, but this is a second case. So we've said no for piecewise functions, and now we're saying no again for rational functions because they actually have two pieces. We have to pick up our finger to trace both pieces of the graph. So we're going to say no for continuity. All right, end behavior. So we look at the left side of the graph. We look at the right side of the graph and we want to see what the arrow is doing, what the Y value is doing. So these are interesting because our left arrow and our right arrow are both getting closer to the orange marker. The orange marker is not going up or going down, it's leveling off, and it's leveling off at a Y value of -3. Y goes to -3, Y goes to -3. So one little note you can give yourself here is that horizontal asymptotes are also called end behavior asymptotes because they tell you the end behavior. All right, and we did see that in the logarithmic and exponential unit where the exponential graphs had horizontal asymptotes and it told us some of the end behavior. So here it's just a little bit easier because they tell you the left and the right side. In the exponential unit, they only told you one side. Here they actually tell you both. So on the left side, it goes to -3. On the right side, it goes to -3. Okay, and that's because our arrows both level off at that marker. Okay, let's see if this other example can go fast. I'm sorry for the length of this video already. Okay, transformations. We have a negative in the front, which tells us that this graph has been reflected over the x-axis, which means that instead of the two curves being in these two corners, they will reflect. So you'll have this one will be in this corner, this one will be in that corner, so they'll be in the opposite corners. There's a 3 on the top, which is actually a vertical stretch of 3. So it's a 3 on top instead of a 1 on top. That's how you can tell it's a vertical stretch. Then down here, the x plus 1, that's like the inside of the function. So that's a left 1. Plus 1 on the end, that's the outside of the function. That's an up 1. All right, so here is our vertical asymptote. We're doing the opposite. So our vertical asymptote is left 1, x equals -1. Our horizontal asymptote is up 1, y equals 1. All right, so I'll go ahead and graph that on Desmos, get some points so I can accurately draw it. Y equals -3 divided by x plus 1, the plus 1 on the end. I'm just showing that my asymptotes were what I said they were. So you can see they all kind of fit. Getting my table in there. I'm recognizing here is my vertical asymptote. I just want to get one more value in there so I have some points that are easy to graph. So -2, 4. -3, 2.5, 0, -2, 1, -0.5. I'll go ahead and do 2, 0 because it's on the table and it's easy to graph. It's also the X-Intercept, so I'm going to need that in a little bit anyway. Okay, so there's, hard time speaking. Those are the points we wanted. Let me go ahead and graph that. All right, so domain is from left to right. I'm skipping this vertical asymptote. I'm skipping that x value of -1. So I say -infinity, skip -1. Range is up and down. I'm skipping that y value of +1. My x-intercept is 2, 0. That was easy. I already saw that on the graph. Y-intercept is 0, -2. There are no mountaintops and no valleys on these, so no max, no min. We'll go ahead and put our stick figures for our increasing and decreasing interval. So this is left forever. We know that our increasing and decreasing interval is based on x values. So that's a left arrow, goes left forever. This is increasing. This is an up arrow, but that's thinking of it in terms of y. I don't want to think in terms of y. So in terms of x, this is getting close to a -1. So increases, it goes off into the abyss. Then we start with a new stick figure right here at -1, because that's a down arrow. Again, that's thinking in terms of y, so I want to think in terms of x. This is an x value of -1. So we're increasing -1 all the way to a right arrow, which is infinity. So this increasing answer is between -infinity and -1. And then we have another increasing answer from -1 to infinity. We don't have any decreasing answers. This graph is not continuous. If I want to trace it with my finger, I have to pick up my finger to trace the whole thing. End behavior. I'm going to look at the left side of the graph. I'm going to look at the right side of the graph. As we look to the left, the y value is getting closer to a +1. As I look to the right, the y value is getting closer to a +1. I remember that because end behavior is approaching the horizontal asymptote, because the horizontal asymptote is the end behavior asymptote. So these numbers are always going to be the same.